Yep, we can see it.
Okay.
Yep.
Right. So as was introduced, this is a talk entitled Owicki-Gries Reasoning for C11 Programs with Relaxed Dependencies. This was a joint work done by myself, Mark Batty, my PhD supervisor, and we're both at the University of Kent, and Brijesh Dongol, who is over at the University of Sussex. So as verification people, quite often we do want to verify some code. We consider it generally something of a virtue to know what one's program does. And we have many established tools for doing that. And one of the oldest is one called Hoare logic. Now, the general premise of Hoare logic is that we feed in preconditions to a statement and we work out what postconditions we get if we run that statement under those conditions. The problem with that is that it requires essentially that our program executes in precisely the order in which we write it. And while this is a nice abstraction and works very well in purely sequential contexts, the reality is that in the running of a contemporary computer program, there are multiple layers of transformation that happen between that source code and what actually executes on the machine. We have to compile it down to assembly, we have to assemble it into machine code, and then the hardware has to actually execute that machine code. And if at any point there is a reordering of some statements during any of those links in that chain, then unfortunately our proof is no longer valid, or at the very least we need some reassurance that those reorderings aren't going to impact the validity of that proof. So suppose we want to model these reorderings of statements that happen rather often. Well, we have an entire field of tools that we call weak memory models that do that. And essentially they will take in a program and they will tell you when line 2 has to execute after line 1 and when line 1 and line 2 might execute either completely in parallel or in the inverse of the order in which we would expect. But the problem with these models is that very often the output is of the form of a collection of what we call executions, which are descriptions of a particular program behavior. They will say, in this execution, we did line 1 and then line 3 and then line 2. And the problem with these is that it's very difficult to verify that a particular assertion holds in a particular execution. It often takes specific knowledge of what those executions look like, what the orderings look like, and what guarantees you get out of them. So we have a technique essentially to combine these weak memory models with a Hoare-style reasoning. And given that this is a proof technique, I'm going to run you through a simple demo because that's going to be a much better avenue to understanding it than trying to understand all the rules individually. So this is the program that we want to verify. We want to know that if we go in with all of our global variables assigned to 0, we come out with x being either equal to y or equal to z. And intuitively, this is because, well, line 1 copies x into z, and lines 4 and 5 copy y into x. And one of these two should probably be either the last thing to run or not invalidated by the last thing to run. So we're going to give this quick program into a system that we call modular relaxed dependencies. This is a weak memory model that came out of the University of Kent here. MRD is going to take in this syntax and it's going to pass it into a forest of trees, which is what we see on the slide here. Now, these squarish objects are what we call events. They represent individual memory accesses. So you can see in A1, we take a trip into the location X and we find 0. In A2, we take a trip into location X and we find 1. These red squiggly lines between them are what we call a conflict edge, and they indicate that two events can't occur simultaneously. So clearly, if we go into the location X and line 1 there, we're either going to read a 0 or a 1, but we can't read both at the same time. These black arrows that go between them represent program order edges. And so they're essentially saying that in the order in which this program is written, the thread on the left, which I'll try to call thread A, will first read from X, then write to Z, then write to Y. Now, MRD is going to do a lot of complex mathematics to that forest of trees, and it's going to end up with these executions. So these are the two that we would really expect to see. There's the one on the left, where in thread A, we read a 0 from X and we copy it into Z. In thread B, we read a 0 from Y and copy that into X. And then finally, we perform the write of Y at the end. The execution on the right is another sequentially consistent execution that we would expect to see. This time, we're going to copy 0 into Z, perform the write of Y, and then thread B is going to pick up that write and copy the value into X. So these yellow arrows are a type of ordering that our weak memory model will give us that essentially says we can't observe the thing at the end of the arrow until we've observed the thing at the beginning of the arrow. These can represent data dependencies or control dependencies, or sometimes even address dependencies. We generally just call this semantic dependency. The dotted green arrow here is what we call a reads from relation. It indicates that event B2 is picking up the value that we wrote in event A5. And so if we want to observe this execution, we have to do A5 before B2. But there is regrettably a third execution that we could observe of this program if we allow reordering of statements that wouldn't impact sort of sequential correctness. And in this instance, we're going to perform the write to Y first. We're going to pick the value up in thread B, copy it into X, and then in thread A, we're going to pick up the value that we just copied into X and copied that into Z. And the reason we're allowed to do this is that if you look exclusively at thread A, there is no reason why it would be incorrect in a purely sequential context to just do that right first. There's nothing that would stop, for instance, an instruction pipeliner from noticing that it has to do a bunch of trips to memory and it may as well do this one first. And so we want a system of reasoning that will allow us to include this third extremely strange looking execution inside our correctness proof. So the Owicki-Gries part is what gives us our ability to reason about separate threads individually. There's a condition called interference freedom, which I will go into later. But the general premise of Owicki-Gries reasoning is that if our proof of correctness for thread A goes from our desired precondition to our desired postcondition, and it can't be clobbered by our proof of correctness for thread B, and separately the same and inverse holds for thread B, then we know that our entire program is correct. So we're going to do some parsing on these executions, and we're going to turn them into what we call a program future. And a program future is basically an execution where we've taken away all of the program order edges, and we only care about the edges that we really have to observe in practice. And you'll notice that two of these are the same. There are two program futures where we pick up 0 at X, we write 0 into Z, and at some point we write 1 into Y. There is one program future where we do the write first, and then we end up picking up a 1 from X, and we end up writing it into Z. So our question now becomes, where in our futures could we be before we execute line 1? Now, if you think of a traditional Hoare logic style proof, the answer to this question would be, well, before we execute line 1, our program counter must be pointed at line 1, and afterwards it will be pointed at line 2. So our precondition is some predicate that we can associate to the program counter value 1, and our postcondition is some predicate that we can associate to the program counter value 2. Over here, we have a little bit more complexity. We have the trivial case where we haven't done anything yet. The first thing we're going to do is line 1. We have the slightly strange looking case where we've done the write to Y of 1, and now we're going to go ahead and execute line 1. And we have the very strange case where we've done a write to Y of 1, and now we're going to execute line 1 and we're going to pick up the value 1. And we're going to treat all three of these cases separately. So what are the preconditions for executing it in these potential program future states? Well, we know that the only things we ever write to X in this program are 0 and 1. So if we haven't observed anything in this thread yet, then we're probably safe to assume that the value in X is either 0 or it's 1, but not really anything else. And if we've performed the write to Y, then we can also assert that the value of Y is 1, because our other thread is never going to interfere with that. Now, obviously, because we haven't executed anything yet in this thread, we would really like to assert that the value we have in X is 0. But unfortunately, we're not allowed to do that. And this is the interference freedom that Owicki-Gries reasoning requires. Essentially, whenever you want to associate a predicate to a state, you have to ensure that any execution of thread B or any execution of a single statement of thread B can't ruin that assertion. And clearly here, if we go into thread B with the value of X at 0 and the value of Y, the value at Y of 1, then we can't come out of thread B with that still holding because it's going to copy Y into X. So we have to loosen up a few of our guarantees. But now that we've got these preconditions, we can start adding the postconditions, which is a fairly simple way of saying, well, if I'm at this state and I do this execution, what has changed? And clearly, if we read the value at X into a local register R1, which is only visible to this thread, we can now very easily assert that the value in R1 should probably be 0. And we can move our state from this have executed nothing to have executed event A1. Similarly, if we have done the write to Y, we can also know that the thing in R1 will definitely be 0 if we execute from this state, because our future tells us that we're about to read a 0. So does this mean that our proof burden starts to really seriously explode? And the answer is, well, fortunately, no. And with my sincere apologies to anyone in the audience who's allergic to categories, we have a very nice result here that effectively we require, because there's no dependency between lines 1 and line 3, then their executions have to commute. So executing line 1 followed by line 3 has to result in the same state as executing line 3 and then executing line 1. So while our proof does fork occasionally, it can merge later on thanks to the requirement that these things commute. So here is really the principal result of this paper. We've taken what would be an incredibly linear proof, and we've said, well, things might not execute in this order, but we can give you a total map of the order that they might execute in. And so instead of having this sort of straight line proof structure, you're going to get this nice little tree where the subtree on the left is what our execution could look like if we start with the assumption that we're going to read 0. The thread on the right is what our execution can look like if we start with the assumption that we're going to read 1. So beginning on the left here, having done nothing, we could either execute line 1 and end up at that statement on the left, or we could execute line 3 and end up at that statement on the right. But after doing either of those, we should be able to sort of merge our program state again by executing line 3 or line 1 respectively. We could also, after executing line 1, move straight on into executing line 2. But again, if we have executed lines 1 and 3, then doing line 2 should get us to this empty state at the beginning, empty state at the end. And if we have executed lines 1 and 2, then executing line 3 should lead us to this empty state at the end. And notice that we actually weaken our predicates quite substantially when we go towards that empty state, because we only require that the postcondition of, say, executing line 2 from the state in which we only have A3 left to do implies the postcondition at empty. So there's one more slightly strange thing that you might have noticed, which occurs in the execution on the right there, which is that we start by asserting that the value of Y has to be 1. We perform a read from X, and only then can we assert that the value of X has to be 1. Well, our futures promise that the value of X is going to be 1, and they do this, and they require that it happens in this order, because this pair of pre and post conditions aren't just describing this particular event, but they're also describing all of the things happening in thread B that we can definitely observe by the time that we get to this event. So here you can see that our correctness predicate, predicate that we associate with this state, which is that X and Y are simultaneously 1, is clearly preserved by thread B, and so we maintain the interference freedom requirement that we get from the Owicki-Gries reasoning. Now we need to do a similar proof for thread B, but the thing with thread B is that it can't actually exhibit any weak memory behavior. Here, the thing it's doing is copying the value of Y into X, and it can't write anything into X until it has definitely read something from Y. So this becomes a standard Owicki-Gries proof, which I'm not going to go through here. So in summary, we've presented here a proof technique that is more tractable than the absolute worst case, because our proof technique doesn't actually branch on every possible ordering, thanks to our requirement of commutativity. And we use a dependency oracle to provide these guarantees of when statements actually can't be reordered. You'll also notice that I didn't describe the functioning of the modular relaxed dependencies model at any point during this demonstration, because it doesn't matter. We can use any dependency oracle we like that gives us some notion of events and orderings between them as its output. We're also capable of allowing non-sequential consistent behaviors. In other words, behaviors when we don't execute lines in the order in which they're written, which gives us an advantage over regular operational models. And we have an operational semantics in the paper that sort of hooks onto the whole logic reasoning, but is guided by the weak memory model that allows us to do this. And unlike getting a fistful of executions back from an axiomatic memory model, we can be goal-directed. We can have a pre and post condition and verify something like a contract for our program. Thank you.
Okay, thank you for the presentation. Are there any questions from the audience? So again, you can chat, you can add questions to the chat window, or you can raise your hand. There is a question here from Malte Schwerhoff. Thank you for the nice talk. Can you briefly compare your work to other deductive verification approaches, such as RSL, FSL, for which a very fast style verifier prototype was published?
As I have not read the publication, I probably can't do this to a particularly great degree of detail, I'm afraid. For us, the main advantage here is that we are, as I said, hooking up with weak memory models, which solve a variety of open problems in this space where we allow reorderings. So we don't marry ourselves to any one solution to that problem, which, again, I haven't read the publication, but that's one thing I would be concerned that they did. And we, for many of these memory models, they will have something called an implementability proof and a data race freedom implied sequential consistency proof, which are two things that that language semanticists really enjoy having when it comes to adding weak memory semantics. So you want to ensure that whatever reorderings you permit are definitely invisible in a purely sequential context. And you want to ensure that whatever reorderings you permit are definitely things that the hardware might actually do. And that things that the hardware might actually do are definitely represented in your weak memory model. So those are sort of the key results that weak memory people like to have. So that's one thing that I would look for as a point of comparison. And then, yeah, it's this agnosticism and this ability to reorder statements being the key point of this approach.
Okay, I hope this answers the question. I also have a question. Did you implement this technique, or are you planning to?
So we have an Isabelle formalization, which I did not touch. That's entirely Brijesh's work. So if you have any particular questions about that, I'd direct you towards him. But we have described the operationalization of the MRD semantics in Isabelle, and we have worked through a few sample proofs of small programs. And I believe we have a brief description of that in the paper. In terms of what tooling is available for weak memory models as a whole to pull out these executions, these sets of things that your program might do, again, there's a variety depending on model. For MRD, we have a tool called Murder, which can take in a program and hand you back a LaTeX document, actually, describing all of these potential executions. I believe the PWT model has a tool as well called Pewter. I couldn't talk with much authority about what tooling other models have, but it's one of the things that sort of is quite commonly published with a weak memory paper is some piece of code that will run the model on an input and give you the executions as an output.
Okay, yep, thank you. If there are no, I don't know if there's any. We still have about 1 minute, but I think we have, it is better to move on, unless there's still a question. Okay, but so thanks again.